Yeah, let's get started. So the term AUTOSAR stands for Automotive Open System Architecture. Let's see how the world of automotive software looks before AUTOSAR. So before AUTOSAR, it's like the OEMs um, were trying to outsource many things to the respective tier one, and they rely completely on the software for a newly developed vehicle or a new feature that has to be developed has been given and like extracted from tier one. Now, in this exchange, OEM aims to improve uh, a driving performance, fuel consumption, emission, their production process, and their time to market, and they have other constraints to be met. But over a period like after after 2000, where OEM started seeing the potential of having a standardized architecture and having reusability in terms of its base software and in terms of the application. So uh, that's how this AUTOSAR consortium is formed. So initially, if you see the whole automotive system, it was completely mechanical. Slowly, when there was a need for meeting the stringent emission norms, so gradually there was an introduction of uh, electronics plus mechanical or electromechanical system started coming into your engine management system, in your safety system and other systems. So then uh, programmable electronics, a programmable embedded system started coming and started supporting your complex mechanical systems. So this is how the whole automotive system, what we see, has evolved. So it's not only the software that is there in the infotainment system or in the instrument cluster. So the vehicle, there is a new term that's a buzzword in today's automotive market. Going forward, our vehicle would be a software defined vehicle, and majority of the things would be driven by software. So that's how the uh, landscape or the ecosystem of this whole automotive uh, is actually expanding. Now in modern vehicle, uh, at least if you take a mid-range vehicle that's launched in India, has got more than 80 plus ECUs, and which reads value from hundreds of sensors, and in fact drives different number of actuators. And it's a very good example, or a best example for a distributed embedded system which are interconnected and exchanging several data at a different latency, and working at a very large scale. So if you take the ECUs in a vehicle, it ranges from adaptive cruise control to electronic braking system to sensor cluster to uh, parking system, airbag, sunroof, and so on. So just give me a minute. Sorry for that intervention. So if you take the functions of ECU, a modern vehicle contain hundreds of ECU doing various functions. And on a broad term, today we see they are classified based on different domain. You have um, your engine power steering controls, your comfort, body control, HVAC, climatic controls. Then you have security access, you have passive safety, active safety. So all for all these application you have ECUs in place. So now let's see and understand why there is a need for having AUTOSAR. So as the name specifies, AUTOSAR stands for Automotive Open System Architecture. So there is a need to standardize and have a open or common system level architecture. So which means it's not only covering um, how a ECU software should be looking like and how a ECU software should be implemented. It gives you more specification and more development methodology to roll out your entire vehicle system. So that is why it is named as Automotive Open System Architecture. So the first requirement is um, there might be different platforms would be used by your OEMs for ECU software. And prior to AUTOSAR, there is a lack of a standard software architecture. Nobody, um, when it comes to exchanging software between tier one and adding a new feature, it was very cumbersome and it was very time consuming for OEMs, which actually was reduced with the help of AUTOSAR. And difficult in OEM is actually facing difficult in uh, transitioning from one supplier to other supplier, and challenges in understanding the existing hardware platforms, then software architecture and standards in the ECU software development, and problems faced by suppliers and OEMs uh, in uh, in driving some of the ongoing project. So these were the need or the reason for AUTOSAR. So actually what AUTOSAR is bringing onto the table. So it is from a processor perspective, it is trying to um, bring the simplification of integration, then the reduction of overall software development life cycle, and switching between vendors and suppliers. So these are certain things that AUTOSAR is actually bringing. Then from a feature perspective, it actually reduces the version, it improves the reusability across OEM, and it allows OEM to spend maximum of their efficiency in functional development. And for tool providers, so there needs to be an existence of common interface and a robust process. So and for market need, some new innovations and rapidly changing technology has to come. So these are the need of AUTOSAR from 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 a semicon to market need perspective. So when this AUTOSAR consortium is started, AUTOSAR Open System Architecture Development Partnership is founded in 2003. So the main objective of this consortium is to create and establish an open and standardized software architecture for the software that is going to get into almost all the automotive electronic control modules. So there are 9 key core partners. They have been driving this AUTOSAR consortium. So started by BMW. There were Mercedes, Ford, GM, PSA, Toyota, Volkswagen. So people across the globe, Japanese OEM, German OEMs, American OEMs, all of them were part of the consortium, and they started driving this project, and they started arriving at how the files and can be exchanged, how this um, software can build in such a way that it is completely robust and reusable. So there were, along with this 9 core partners, there were 56 premium partners and development companies, and 2 strategic and 44 associate companies. So this numbers keep on increasing as we keep on as we progress. And um, but every time, like every year, there is a revision that is happening on the specifications for the software development. And now almost it's been 2 decades where AUTOSAR has seen several version changes and several revisions. And the classic AUTOSAR has grown like anything. And now they have introduced one more architecture, which is not replacing classic, which is actually adding or supporting or aiding some of the special features which is not addressed in classic AUTOSAR. So that is adaptive AUTOSAR. So for or what is the benefit for each of them? So AUTOSAR supports automotive OEMs to tier ones to suppliers in terms of improving the ECU software quality and to reduce the development cost, as well as it avoids the reinvention of wheel. So which means you don't want to redevelop a similar ECU software component repeatedly for the same application features. So what they want to establish or achieve through AUTOSAR is the application software should be pluggable, plug and play kind of a thing, which means the software that I have used in my previous version, the same application software, I can do some little modification and I can reuse that completely in the upcoming version also. And the kind of standardized base software modules also should be reusable. So portability of your application software component and reusability of your base software. So these are the two objectives when they lay down this architecture. So in simple term, what is AUTOSAR? So AUTOSAR architecture consists of like many abstracted layer, um, and that tries to isolate your application completely from the hardware. So today we see the most advanced version or advanced architecture in our mobile phone. So where you can see the hardware and software is completely isolated, where the software updation can able to happen seamlessly. And the application that you load onto the platform is completely what do you say, independent of the hardware. So they want to attain, our AUTOSAR consortium want to attain these kind of similar architecture for vehicle issues. So with that objective is what this has been started, at this architecture was formulated. So once in the initial stages, like they were trying to address, or they were trying to um, meet the two requirement which I already told. One is the application should be portable across ECU, which means the ECU, the application that I have used or that I have built as part of my previous ECU or my previous version ECU, I can take it to the future versions or the next generation ECUs also. So that should be one requirement. It's not 100% a OEM is going to replicate the same software in the next version, but wherever it is possible, they want the application to be portable. The second is reusability of this basic software. So if with minor changes and minor configuration, this basic software, once it is written, it has to be reused again and again. Let's say, for example, you have a microcontroller, you have you are running a CAN stack on top of it. So this CAN stack, depending on your application, it has to be customized and configured. Every time I should not build a new CAN stack. So that was the idea. So to meet these two requirements, they have formulated this architecture. So the architecture goes like this. So there is the view that you are seeing is the not a detailed view. It's a very high level course view, where you have a basic software, and on top of basic software there is a runtime environment which allows your application layer to completely become independent of the base software component. So these three layers are further bifurcated into many other layers. So here if you see, the application software interacts with base software, and base software interacts with hardware through some interfaces. These are the interfaces which is actually standardized and l- derived or put forward at the time of setting of this architecture. So AUTOSAR, what if in a single term, if you want to explain what AUTOSAR is defining, AUTOSAR is giving you some set of APIs which you have to implement so that your application software component, base software component, and hardware, all these three interacts using that interfaces. So they standardized the interfaces, as well as they are given some predefined rules of the interfaces. So if I break down uh, into a detailed view, it goes something like this, where you can able to see the base software is divided into sub modules, many sub modules, and three or four layers, I would say. So there is a separate layer which connects your RT and MCAL directly, and it's called as complex driver. And there is one dark purple color layer that you have, which is called as a microcontroller abstraction layer. And then you have other layer, which is this one. It's called ECU abstraction layer, and you have the other layer, one other layer, which is called as system services layer. So our the services layer. On top of this, you have your RTE and your application. Okay. Sorry for that intervention again. Now let's try to break down and see the or understand the functionality of each of these layers. See, the AUTOSAR layer, as I told you, the basic software layer consists of several software module that is structured in the different layers as per the standard produced or standard given by the AUTOSAR consortium. And the AUTOSAR application layer is the top layer of your AUTOSAR, and this layer is a or this layer will contain the core business logic or the core custom feature implementation. So this is specific to OEM, and um, the OEM derives the software component. The OEM shows all the difference in implementing their own software component, or other base software, are something that is standardized and that is in fact available in the market as a half the shelf product, which means there are vendors in market who is available or who is selling this whole base software as a product. You can buy the off the shelf product from them and you can customize accordingly. So now let's try to see the evolution of AUTOSAR. So the classic AUTOSAR uh, development started with addressing certain agenda. But as we move forward, as I told you, there were some need or some special features to be accommodated. The objective still remains the same. The objective here was to completely isolate the application software from the hardware. But the challenge is, whereas the classic AUTOSAR addresses how we can able to scale, transfer those things, but there are some missing things which is not addressed in classic AUTOSAR. Like if you want to upgrade your software dynamically, upgrade base software or upgrade an application, and those over the air update kind of a feature, and how to use a high performance processor for for your ECU application. So that is, those things were not addressed in the classic AUTOSAR, and the idea of moving towards adaptive AUTOSAR is where we have some special needs of certain product lines like driverless cars, autonomous features, your very heavy um, infotainment system. So these requires a different kind of hardware infrastructure and the development cycle. So that's where your adaptive AUTOSAR started coming into picture. So we have discussed about all these three views. So this is a top view, this is a course view, and this is a detailed view. Now we will try to understand the functionality of each of these um, layers. So the microcontroller abstraction layer is the layer that is very close to your microcontroller, and it contains the drivers, or it contains the driver logics of all the peripherals that is residing as a on-chip peripheral of your microcontroller. So here's, we will try to see description, task, and properties for each of the layers. So one is as far as MCAL is concerned, which is MCAL stands for microcontroller abstraction layer. So as far as MCAL is concerned, it is the lowest layer of the basic software, and it contains drivers uh, which allows you to access, or which allows the upper layers to access the internal peripherals of the microcontroller. So the task of MCAL is to make higher software layer independent of your microcontroller. So this is the key task. So if you are replacing your microcontroller, you just have to go ahead and change the MCAL completely, because MCAL is a layer that is completely dependent on the microcontroller, whereas the functionality is to make the upper layers independent of the microcontroller. So tomorrow, if I'm changing the microcontroller, I don't want to go ahead and replace all the other layer or all the other codes. So essentially, if I change the MCAL, the integration should be seamlessly working. So the MCAL module is further broken down into several subgroups, or group of several like similar module. It is it has microcontroller drivers, memory drivers, crypto drivers, communication drivers, and wireless communication drivers, IO drivers. Now, as part of your microcontroller driver, we have MCU, watchdog, timer drivers. Then, as part of crypto drivers, we have drivers for the HSM module, hardware security module. As part of communication, the standard communication that is supported in the automotive, like CAN, LIN, FlexRay, Ethernet, and SPI. Then you have wireless communication drivers, which is used in the V2X communication. Now, moving ahead with the next layer. The next layer is ECU abstraction layer. So ECU abstraction layer is typically the second layer of your basic software. So let's see the same three things. Uh, the definition of ECU abstraction layer goes like this. It gives you interface between uh, the drivers of the MCAL, as well as it offers some set of API that allows you to access the external devices, which means your application or your above layers doesn't know that these devices are part of your microcontroller, or these devices are connected externally. So just to give you an example, let's say you have an external CAN controller connected, or you have external EEPROM or a flash memory connected. So the upper layer uses the API defined in the ECU abstraction layer, and irrespective of the ECU layout, the upper layer handles it in the same way. So using this set of APIs, we use or we take care of abstracting the devices that are connected externally to the ECU. So the task here is to make higher software layers independent of the ECU hardware, and the properties goes like this. It makes or the this layer itself is microcontroller independent. But it is dependent on the ECU hardware. So if your ECU is connected with 10 different external peripheral devices, so the drivers for those peripherals is abstracted in this layer. Yeah, sorry, I'm back. So the property goes like this. As I told, it is microcontroller independent, but it is dependent on the ECU hardware, whereas it makes the upper interface uh, completely independent of microcontroller as well as ECU hardware. So collectively, using your ECU abstraction, you can form a stack. So that's called as IO hardware abstraction stack. So just to give you example, let's say your application wants to read a value through a ADC channel, or your application layer wants to write a value or write a data uh, to the microcontroller or through the IO channel. So in that case, you will be having IO hardware abstraction module, IO hardware drivers part of MCAL, and this IO hardware abstraction part of your uh, ECU abstraction layer. Then on top of that, you have the RTE and the application. So it offers you a wide range of our standardized interfaces. So which helps in abstracting what is happening inside or what is the code inside. So here the definition goes like this: any peripheral or any IO devices that is connected to the peripheral can be accessed by your application layer through RTE using this IO stack only. So our IO hardware abstraction usually consists of these components which are part of each of this layer. So as part of your microcontroller, we use ADC DIO peripheral as part of our EC abstraction layer. We will have IO signal interface. Then we had like similar to IO hardware abstraction, we have communication hardware abstraction. This allows to like abstract the communication devices. Then you have memory hardware abstraction also. So here is an example. Let's consider a ECU has got um, an ECU is using two CAN controller. So where so like microcontroller has got only two internal CAN channels, and additional CAN channels are coming from, our controllers are coming from the onboard ASIC. So the CAN ASIC is connected to the microcontroller through SPI channel. So the communication drivers or the communication hardware abstraction will help you to handle, or will help the application software to handle the data that is flowing through the internal CAN channel and the external CAN channel in the same way. Then you have memory hardware abstraction. The same way, the data that is returned to internal memory or external memory is handled via the same mechanism. Then coming to the next layer, or part of our next entity that is part of your basic software. Here it's called as complex device drivers. So the definition of complex device driver, uh, it's the only module that spans, or that allows your application to directly interact with the microcontroller. So through RT. So the task of this particular layer is to provide or accommodate some of the high timing critical application, or if you have some old legacy code and you want to bring those legacy code inside the AUTOSAR project, inside the AUTOSAR project, those things are um, done using complex device drivers. So if you see the complex device driver, the complex device driver can contain um, application component, or base software component, or any part of the legacy code can be accommodated in the complex device driver. So it might be application, as I told you, the upper interface can also be application, or can also be hardware dependent code. So then, as a fourth entity of your basic software, you have services layer. So this services layer does several functionality. So the definition goes like this. This is the highest layer of your basic software. So which also applies in the relevance of the EC abstraction IO signal that we have seen. So the task of this is to provide some of the basic services to the application. So your application sometime require different services. It can be OS scheduling services, or diagnostic services, or memory related services, or communication related services. So all these services are accommodated by the modules that is there in the services layer. Let me detail out all the services that is offered. So as I told you, it offers memory services. Memory services is done or handled by a module called as NVRAM manager. So this NVRAM manager is responsible for managing the reading and writing of non-volatile data from your application, or to back to the application. Then we have set of system services. So you can able to see what are various system services that is actually offered as part of your service layer. You have AUTOSAR operating system, which takes care of all the OS related things. Then you have diagnostic event manager, function inhibition manager, default error tracer. Then you have like time services, watchdog manager, ECU state manager. These are different services which is offered as part of your system services. So the task is to proceed or provide the basic service for the application software. So basically, the application software that is above RT avails these services from the services layer only. So then we have communication services. So for this, there is a module called as COM service module. Then you have some IP transformer, you have AUTOSAR COM, diagnostic communication manager, and you have IPDU, PDU router. All these modules are responsible for offering communication services. So what do I mean by communication service? When an application wants to send a data outside the ECU, so that that data is given or shared to some other ECU through some standard protocol like FlexRay, LIN, or CAN. That is, in that case, it is the application will avail the services from the communication services module. So the task here is to provide a uniform interface for the uh, entire vehicle network, be it CAN, be it LIN, be it FlexRay. It's like all the data transfer mechanisms are treated in the similar way with the help of this communication services. Then you have the like most complex layer of the entire AUTOSAR ECU, which is AUTOSAR runtime environment. As I told you, this runtime environment is a layer that completely isolates or that completely makes your application module independent of the base software and the below layers. So if application layer wants to avail a service from the service layer, it needs to um, get that through RT only. And if your application layer has to talk to or send or avail a service from other software component, even in that case, it has to avail the services from RT only. So here are the definitions of RT. So RT, as the name specifies, it's you can equate RT with the kind of a Java runtime environment which runs on top of your Android or any other platform, so that your Java application seamlessly runs. So here also, this RT provides as a base for the C application that is on top of the um, um, or that is part of the application layer is is running seamlessly uh, without and with this RT only we make the application software component completely portable. So it provides communication services to the application software, which means if two application software want to exchange some value, even in that case RT is used, and it makes AUTOSAR components completely independent from mapping to a specific issue, because due to the existence of AUTOSAR RT only, your software components became plug and playable across different ECUs. And very importantly, this AUTOSAR runtime environment is not handwritten; it is machine generated, or it's generated by the respective uh, tool, and it needs to have information about your service layers, components, and it needs to have information about your CDD, needs to have information about your ECU abstraction, the ports through which your application is interacting with the below layers. So with having all this information, this AUTOSAR RT is generated through the tool, and it is different for, or it is unique for each of the ECUs depending on these things. So the implementation here is ECU and application specific. The RT is purely based on the ECU modules and application specific, and it makes the upper interface completely ECU independent. Now coming to the a last layer, a top layer of our um, architecture, AUTOSAR architecture, which is application layer. Now, so here you have what do you say? Till this layer, the the code is based on modular arrangement, which means there is a layered architecture one over the other. But in the application environment, it is purely based on component style. So which means it is not a layered arrangement. So this application software will run parallelly, or is executed or is scheduled by your scheduler. See, the AUTOSAR application layer uh, includes various application specific software components. So that is designed to execute a specific uh, set of tasks as per the requirement. So what you can see or what you can visualize as an application, let's say there is a software component which actually estimates how much amount of fuel that has to be injected uh, into the PC, or sorry, into the engine. So that calculation is derived, or it is coded as your, or will be part of your application layer. And as I told you, this there is a big shift in the architecture when it comes to the application layer. It is not a layered structure, it is component style of structure. So your application layer will contain three important part. One is the AUTOSAR actual software component implementation, the code itself. Other one is ports and interfaces. So these ports and interfaces are the mechanism through which your entities inside the application layer communicates with each other or communicates with the below layer. So in short, if your application wants to interact with or exchange any values with other software component or with the below layer, it interacts through the port. So that's about the entire layered structure and task functionality of each of the layer. Now we'll discuss about the methodology. So how the whole AUTOSAR development is being done across the system or across the entire vehicle. So the initial approach is to at a architecture level create the detail of all the software component description. So you will have several software component that is designed for the entire vehicle, and they are interacting with each other through the virtual functional bus. So here if you see there are there is an AUTOSAR software component 1, software component 2, software component 3, and each of these software components are interacting with each other through ports and through the specific interfaces via the virtual functional bus. So which means the architect will assume something as virtual functional bus, and he starts writing or putting down the details about all the software component. Then the second detail or the second level is they break that information or they map the software component to the respective ECU, which means let's say here software component 1 and 2 is mapped to ECU 1, software component 3 is mapped to ECU 2, software component N is mapped to ECU N. Then they have details about how ECU1 and ECU2 and ECU3 are interacting or communicating with each other. So accordingly, they'll create the respective base software and they'll configure the message from the software component goes out. So your virtual functional bus is finally implemented as RT in most of the cases. In certain cases, this virtual functional bus is replaced by the real bus along with the real communication stack. So when we start this process, this whole thing is created at a high system level. That's called as your uh, system configuration description. So we take system configuration input and configure and create a system configuration description. So the next step is, so you can see this is what happening at system level and this is what happening at the ECU level. So mostly the entire system is owned by OEM. The system level activities are mostly owned by the OEMs, whereas the ECU ownership lies mostly with tier ones. So each tier one is responsible for implementing. Excuse me. For implementing the necessary basic software, RTE, and the application for each ECU. So the cycle goes like this. So the very first step is mapping the software components to the respective ECU. So here, before that, we have to define, or the architect has to define at a system level, the architect has to define how many ECUs are there, what are the software components are there, and what is the network topology on which each of these ECUs are connected. Then finally, they will create a file that is representing the system information, including all the ECU, bus mapping, and topology. Then once they have created, this file is called as system extract or system description file that contains detail about the entire system. Then they create something called as the extra. They'll take out the information associated with one particular ECU, and this one particular ECU information is passed to the next level, to the next layers, or to the next part of the development. So let's see that in the detail with a short animation. So what you're seeing here is um, tier 1 is having AUTOSAR ECU development tools, and OEM is having AUTOSAR system development tools. So they define the software component. Then so that software component definition is exported as software component description file, and it is passed or it is imported to a model based development tool, and the code is generated, or in certain cases the code is handwritten also. So using certain development tool, the code is handwritten. So finally, the software component implementation is done. You will have legacy and coded files, or the software component file that is generated from your MBD. So these are two alternative approaches. For doing this, you need to have one file as input, which is your software component description. This software component description is usually defined at the system level. Then they will distribute the software component. So in this step, we'll come to know which software component is going to get into which ECU. Then they define network. So in that case, in the defining the network, they will address uh, which ECU is connected with which ECU through which network and how they are exchanging information. So finally, as part of the AUTOSAR system development tool, we have created an entire system description containing all these three details. and you have created software description, which is used for creating the or implementing the actual software component alone. It's not the entire ECU software, it is only the application software. Then using the system description, we take the ECU extract information or one ECU information alone from the system description. So if let's assume if a vehicle has 100 ECU, so system description will have details of all 100 ECUs, whereas the ECU extract file will have detail about one ECU which you have generated particularly about that ECU. So once you have generated the ECU extract file, this ECU extract file is given or passed to the tier 1. So what he will do, he will identify, he will integrate and validate the software component along with the RT configured and the BSW configured. So what he'll do, he'll take the ECU description file, and then he'll take BSW module description, then he'll create um, the ECU extract, or using the AUTOSAR ECU development tools, he will create he will attempt to the OEM, sorry, the tier 1 company will attempt to integrate the generated application software and validate the application software along with RT and BSW. Then finally you'll generate the software code involved in RT and BSW. So this is the work that has happened or that is happening on the ECU side. So here he'll add specific information about task scheduling of basic software, and he'll configure all the ECU configuration modules. Module wise he'll configure, then he'll generate all the source files. So each of the module will have the respective code generator to generate the code. So the code will have cfg.h or lcfg or pbcfg.c.h file. Then this is called a generated code. Then the tool also will have static code, which is called as canif.c, canif.h. Then we compile these two things together to produce the final executable. Now our application is ready, the previous case, and our application code is ready, base software code is ready. Then with all the information that we have, which means with ECU configuration details, software component description, and service component description, we pass all this file to RT generator to generate RT. Now RT is there, application is there, and the software component is the base software modules are there. Finally, it is integrated along with the static and the generated code, and it is compiled to create one compiled link to create one final executable that has this all these components together. So this is called as AUTOSAR methodology, or in short, this is what happening at a methodology level. With this, we have quickly seen what is the AUTOSAR layered architecture, and what is the methodology that is followed when it comes to the what do you say um, rolling out an AUTOSAR ECU software from the entire vehicle level details. So we can take up questions. If you have any questions, please feel free to put it in the chat window.
Mr. Jegan, there are questions in the chat window.
Yeah,
Would you?
let me take it. Yeah,
Yeah.
I'll take one by one. Let me stop sharing. Okay, I think there are a lot of questions. We'll go one by one. Sari is asking, So if we change hardware, only MCAL layer changes are there, right? Um, there are possibility. Yes, you are right, Ari. 100% we have to change the MCAL if we are changing the uh, hardware, but there might be impact if you are using a CDD module. Even that has to be changed, or there might be impact because of hardware change. And if you are using uh, OS, certain part of your OS is aligned to the memory map of the microcontroller, so that also has to be changed, or that also has to be customized. So AUTOSAR OS porting part has got some dependency. That is why in this, so in this layered architecture, if you see your let me come to this. Your services layer is also touching the microcontroller. CDD is touching microcontroller, and MCAL is touching microcontroller. Any change in microcontroller will have impact on these three, but these are minor, whereas your MCAL has to be completely changed. I hope I answered your question.
So Jagan, you stay on the screen itself. I can read out the questions.
Okay, okay.
Yeah.
Yes.
So question from Karthik is, in testing, which layer can be used in AUTOSAR?
In testing,
Testing.
come
Yeah. Testing.
in testing, which layer of the AUTOSAR
Which
is
layer?
used?
Yeah.
Okay. So let's say, for example, if you want to test the functionality of your application, where your application is writing data to the memory, then you need to incorporate all the layers involved in memory stack. Let's say in the case uh, if you are writing a data to the communication channel, or to CAN or LIN channel, then you need to have the respective CAN stack or LIN stack. Uh, so to test, you need to have other modules can be stubbed, but the basic functionality which you are trying to uh, test, so that entire stack should be there, starting from application RTE, and the entire stack should be there.
Thank you, Jagan.
Yeah.
So Hari again asks, when we write application software, the RT layer generates automatically.
Uh, so RT generation happens in two different phases, Hari. One is called RT contract phase. Other one is the RT generation phase. When you write application, the RT will not automatically generate. I think you are telling if you are implementing the software component inside Simulink kind of an environment. In that case, what you have to do is, you need to, in your model, you need to make certain changes. You need to define your interfaces. Then you need to generate code with respect to uh, what do you say, uh, the AUTOSAR coder, or with using AUTOSAR coder. Even then, the RT headers alone will be generated. For generating the complete RTE, you have to follow the RT generation process, which means you need to have ARXML files about the application, about the service after component, and about the OS related things. So with having all this extract, you have to generate the RT. RT is not automatically generated when you write or when you implement the application. So in the MATLAB, the files that you see, it is only the RT headers, not the complete RT implementation. Yeah.
Thank you, Jagan. Next question from Ravi Kiran is on. Please explain how AUTOSAR layers interact with the underlying OS such as Linux or RTOS.
Okay. In AUTOSAR, you don't have, in classic AUTOSAR, you don't have Linux nor FreeRTOS. Rather, the AUTOSAR service layer itself has got a operating system which is based on an operating system called OSEC. and it is the specifications are derived from Mosaic, and the name that we have given for this operating system is AUTOSAR operating system. So this AUTOSAR operating system uses the APIs that is defined by the AUTOSAR specification. So directly it offers all the OS related features, like it allows scheduling. It schedules the application through RT events, and it supports timers. It has spin lock mechanism. It has um, mechanism for availing shared resource. So it as a OS, it offers all the features. To answer your question simply, um, we use AUTOSAR defined OS APIs to interact with your to interact with the um, or that makes your application interacts with the OS. But classic AUTOSAR doesn't uses any Linux or FreeRTOS.
Thanks, Steven. Next question. Can you explain what is a virtual function bus?
Okay, so virtual function bus is used while creating the system extract. So the virtual function bus is just an indication at a very architecture level. It is not something that is physically existing. So as a architect, software architect, what I'll do, I'll assume there exists a virtual function bus which will allow my software component to exchange data seamlessly. With that assumption, I'll create the high level architecture. Then during implementation, what we do, this virtual functional bus is implemented either as a RTE, or it is represented in the form of communication module, the respective communication module, depending on which software component is, whether the software components are within same ECU or across different ECUs. So virtual function bus is just a imaginary bus which is not finally, which is not implemented as a C code, or you can see, or you can understand the virtual function bus at system level is implemented as RT at ECU level.
Thank
Hope
you,
that
Jegan.
answers.
The next question is from Karthik. He wants to know what are some of the system development tools. Can you name
Okay,
some?
okay. Uh, from a tooling perspective, AUTOSAR uses two tools. One is AUTOSAR configurator, other one is AUTOSAR authoring tool. We use AUTOSAR authoring tool to author either ECU extract or a system extract. If you want to change any uh, any ARXML details, then we go for AUTOSAR authoring. Your application ARXML can be created. Your software component ARXML can be created. Your system level ARXML or ECU level ARXML. All these ARXML can be created using AUTOSAR authoring tool. The example for AUTOSAR authoring tool is your AUTOSAR so vector DaVinci developer. Then you have in inside MathWorks, you have a tool for planning this architecture thing and extracting that as ARXML. You can use prevision, and again from vector you can use um, there is a dspace tool uh, for generating this information, or it as isolar a. All these are for AUTOSAR authoring. When it comes to the base software configuration, you have AUTOSAR configuration tool, like your which allows you to configure all the modules and the respective parameters, and allows you to generate the code. In that case, you use what do you say, uh, tools like Vector DaVinci Configurator, EBTresa Studio, again ETAS Isolar B. So these tools are composed for KSAR. These are some of the tools that is used as the AUTOSAR configurator, base software configurator. Yeah, Venkatesh.
Thanks, Jegan. Yeah. Uh, Ar- Anju Krishnan wants to know what exactly is meant by legacy in AUTOSAR.
Okay. So let's say for example, your company has started following AUTOSAR from today. Whatever that you have created prior to AUTOSAR, which means, let's say, I would have created lots and lots of code before AUTOSAR also. Before AUTOSAR also, every OEM is generating or building their ECU software. All those ECU software that were built before AUTOSAR were called as legacy. So legacy ECUs, legacy codes, which means these are codes which are built before AUTOSAR and which are still in usage. So we are not completely throwing them all of them, because from today I started following AUTOSAR, let me throw all the legacy codes. It's not the way. What we are doing, we are taking those legacy codes and we are finding some way to reuse it through complex device development. So legacy is a term which means that is existing before AUTOSAR also, or that was existing before AUTOSAR. uh, After AUTOSAR, you have this AUTOSAR structure. So wherever you find the term legacy, legacy tools, legacy code, uh, a legacy method, all this indicates what are the things that you had before AUTOSAR coming in.
Thanks, Jagan.
Yeah,
There is a question, a couple of questions about getting the PPT or the recorded session. I'll just answer that. Uh, Myresh, like we will be sharing the recorded session on your email. Please don't worry. Then next question is
yeah.
from
1 minute, 1 minute, 1 minute. I just want to show one resource where you can download all the presentation, because AUTOSAR, as the name specifies, it's an open standard. Nobody is restricting. Whereas these are uh, like I would say, referenced content from the open standard only. You can directly go to the autosar.org and you can download all the documents for free. It's not cost. There is no cost involved, or there is no registration involved. Let's say for example, if you want to start AUTOSAR, classic AUTOSAR, you can look for this particular document, AUTOSAR layered architecture. This for any beginner, this particular document will serve as a best reference document. It is around some 160 pages. Yeah, 180 pages. Talks about the entire this presentation talks about the entire classic AUTOSAR platform. So many of the concepts that I have spoken were derived from this presentation only. So you can still refer this. You don't want to ask presentation from us. Hope that answers.
Thanks, Jigan. We will also send you the recorded sessions from the current session as well, if that helps. The next question is from Prasad. Is IOHW depends on both ECU and microcontroller?
Yes, IO hardware abstraction is dependent on both, because you might have an external ADC, or you might be using an internal ADC. So there is a dependency on the ECU as well as the microcontroller.
Thank you. Mani asks, where do we use MATLAB CodeGen in AUTOSAR?
Okay, so the application software component implementation, right? It can be either hand coded, or you can use MATLAB for converting your models into code, that too specific to AUTOSAR. So in simple terms, your application layer is built using model based design approach. You can use any model based design tool. In that case, 90%, more than 90% in the market, people are using MATLAB related tools. Yeah.
Yeah, Lakshman wants to know how vector canoe is helpful for AUTOSAR.
Okay. See, Canoe is a tool that allows you to simulate the entire vehicle CAN network, and you can create DVCs, the CAN database file. This CAN database file is nothing but it represents, or it is used to represent the entire network topology. So at a system level, you are defining the topology, right? So in Canoi tool, this topology can be represented in the form of DBC. The .dbc file can be converted into ARXML file and can be integrated as part of your system stack. So that is one use case at system level. At ECU level, let's say you can use CanCase Excel tool, and you can use Canoi CAPL scripting to generate CAN messages as well as to read CAN messages uh, to your AUTOSAR ECU or from your AUTOSAR ECU, which means from my application I am writing a data which is thrown into the CAN network, and I want to read the data. I can connect, instead of having other ECU, I can connect a CanCase Excel hardware, and I can automate this whole process by writing CAPL scripting. So for this, I need to have Canalizer or Canoi tool along with CanCase Excel or some sort of VN series hardware from Vector.
Thanks, Jegan.
Yeah.
A follow-up question to the earlier one. Ravi Kiran asks, is it possible to make any AUTOSAR version interact with a new OS or RTOS?
It is possible to interact. Okay, fine. So in the new architecture where we are actually heading, uh, for, we will be seeing a mix of classic adaptive stacks running onto the same machine. Let's say, for example, your adaptive ECU uses some sort of Linux or QNX or any POSIX based OS, and you might be having a um, uh, high performance processor like a heterogeneous SoC. On top of that, you might be running a hypervisor. On top of hypervisor, you might be running a classic stack as well as adaptive stack. Even in that case, the communication between them happens through some sort of standard communication or some sort of the standard peripheral. It is like in heterogeneous, yeah, SoC. How do you transfer, or how do you exchange values between your A series core and M series core? It's on the same way. That is how, or that is how it, if we, these scenarios will come into real if we 100% migrated towards the zonal architecture from the distributed architecture what we are seeing. So only through classic AUTOSAR, we doesn't have any requirement or need as such. Whereas combination in future, we will have combination of adaptive AUTOSAR stack, classic AUTOSAR stack running on same powerful ECUs or running on two different ECUs. So there we will have this need.
Thanks, Jegan.
Yeah.
One final question. What is an ARXML file generated from MATLAB? Does it have any link in AUTOSAR?
Yes, it will have link in AUTOSAR. So the generated ARXML file will have details about the software component. Um, uh, let's say, for example, it will have detail about um, the entire software component description. So which means it defines what are the ports that is used, and what are the interfaces that is used, and what is the data type, what are the functions, and what are the arguments used. So that ARXML will have details of all this information, and this is very very important file for generating RTE. So without this file, we cannot able to generate RTE, and without RTE, we cannot able to integrate all the software component into the ECU.
I think that's all the questions. There was one question about any advice for freshers who want to get into automotive software development.
Okay. So as a fresher, if you want to get into automotive software development, please be mindful that you have to be more than having a domain skill. You should be a solid programmer, solid embedded programmer. You should know one 32-bit architecture. You should have aware of one operating system, um, one real-time operating system, and you should. It is good that if you are exposed to embedded Linux concepts. I would say these three things are mandatory. Or if you have not exposed to embedded Linux concepts, you should have exposed to model based development. And if you are coming from mechatronics background, or if you are coming from automotive background, even then you can get into the application development side.
Thank you,
So
Jegan.
yeah, as a fresher, one can be open to get into either application or either get into base software. So the market is very big for accommodating uh, freshers, and people are uh, taking freshers for these kind of roles. All the best.
Thanks, Devon. That helps. Thanks everyone for joining in. We'll take another couple of minutes to introduce a newly launched course in partnership with Electrobit. We have launched a Classic AUTOSAR Professional Certification Program in partnership with Electrobit. I'm just sharing my screen. It will not take more than 2 minutes. I've also shared a feedback form on the chat window. I request everybody to take a couple of minutes to look at it. Jagan, hope my screen is visible.
Yeah, it's visible, Venkatesh.
Yeah. So, yeah. So it is a virtual instructor-led program. It's about 40 hours of sessions spread over a 4-week period, and it comprises of 9 modules. In a minute, Mr. Jagan will go through the modules and talk about it. It also involves hands-on learning. The most exciting part is you get a 45-day license for the Electrobit tool, EB Tresor WinCore 8 and EB Tresor Studio tool, and it helps you with all the hands-on stuff as well. Right, so we have just closed one batch in this program, open batch from 3 different companies, and 4 individuals had also joined it. Our next batch for this starts on November 27th, post Diwali. We are hoping to close the batch by the end of next week. Right, so if you are interested to know more about this program, there is an option to check a box in the feedback form. We'll make sure to connect with you. Mr. Jagan, can you please go through the modules and talk about the significance of this course?
Yes, yes. So as Venkatesh pointed out, the challenge in learning AUTOSAR is the tool infrastructure. So it's very difficult to have tool, and from a development perspective, it is very difficult to demonstrate one simple hello world concept also in AUTOSAR, because even for that you need write application from there till MCAL. So and hello world or LED blinking kind of application also very complex to be demonstrated. So with that, what we have done is we have created many unique examples, and we are demonstrating all those things as an hands-on uh, using our EB Tresas tool. So the participants would be getting access to the license of EB Tresa Studio as well as EB WinCore tool. So and you can try out all the exercises which we are demonstrating in our live class. So the focus here is to introduce uh, the concept of AUTOSAR integration. So we start giving details about AUTOSAR overview and methodology. Then slowly we will talk about the application RT, and how to create your own application ARXML, and how do you create your ECU extract, and how do you generate a basic code that runs on a microcontroller. And the tool also has a virtual way of simulating the software that you have created, because it uses WinCore where the entire MCAL is dubbed. So you doesn't require any costly hardware for seeing the output. You can see the configured output in the tool itself. Then we go ahead up and explain about CDD, like how do you use CDD, then IO hardware abstraction, COM stack, memory stack, diag stack. So and finally we end the course by introducing what is adaptive AUTOSAR, and uh, there would be hands-on session on IO hardware abstraction, ARXML creation, software component integration, RTE generation, then COM stack, diag, then memory. You have, so it's, I would say it's a 60 are 70-30, 70 percentage of hands-on with 30 percentage of theory. So we believe like more practice that you do with the tool, you get good insight about the AUTOSAR implementation. And the outcome here is to um, convert somebody in level 0, level 1 to become a proficient AUTOSAR integrator. And finally, we also give a integrated course project where they have to uh, do implement and integrate an application involving CAN and memory stack. So that's about the program in a nutshell. So if you feel it's very difficult for you to get hands-on in AUTOSAR, you can try out this program. And the license is not hosted in the cloud or anywhere. It would be given to you. You can install that in your personal laptop, and you can spend maximum amount of time in that 45 days. It's not restricted, or it's not time bound. It is I would say it's a node lock license which is given to you for 45 days, and the program runs for 20 days, and remaining 25 days you can take our support, you can practice with the tool,